Welcome to today's explainer. So have you ever actually stopped to think about how modern NoSQL databases process just absolute mountains of information? I mean, we're talking literal petabytes of data here, and they do it without completely crashing. Today, we're popping the hood on the modern internet to explore the actual engine making all of this possible, the MapReduce Framework. Just think about the sheer crushing scale of big data for a second. It's kind of chaotic, right? You've got millions of sensor readings, endless streams of global logistics, a never-ending flood of e-commerce transactions pouring in every single millisecond. So how do you process a petabyte of that unstructured, chaotic data without just absolutely melting a server? Because if you try to force all that through a traditional system, it simply breaks. No way around it. Okay, let's take a breath. To solve this, we needed a completely fundamental shift in computing. Historically, the go-to answer was vertical scaling, just throwing more CPU and RAM at a single massive relational database. But eventually we hit hard physical hardware limits. You literally just can't build a bigger box. So modern NoSQL systems rely on horizontal scaling, or sharding. We logically partition the dataset and distribute that workload across a massive cluster of everyday commodity servers. But the real puzzle here is, how on earth do you coordinate a single query across all that chaos? Well, here is our roadmap for today's explainer to figure that out. We've got 1. The Big Data Challenge. 2. Enter the MapReduce Framework. 3. Phase 1, Map Function. 4. Phase 2, Shuffle and Sort. 5. Phase 3, Reduce Function. And finally, 6. The Distributed Power Payoff. Okay, let's dive into this. Section 1. The Big Data Challenge and the Limits of Traditional Databases. So, traditional relational database management systems, they were built on these really rigid tabular constraints. We're talking fixed schemas and heavy mandatory multi-table joins. But when you were dealing with massive volumes of semi-structured or totally unstructured data, those strict rules become a severe immediate bottleneck. Single server upgrades just hit a wall. The only way forward is parallel processing. You absolutely need to run operations concurrently across highly distributed clusters. Section 2. Enter the MapReduce Framework and distributed processing.
Let's lock in on a definition. MapReduce is a conceptual framework and software development model utilized by modern NoSQL databases. We're talking heavy hitters like MongoDB, CouchDB, and the Hadoop ecosystem. It processes massive datasets using a parallel distributed algorithm right on a cluster. Essentially, it's a divide-and-conquer strategy. It takes a massive task, chops it up into smaller subtasks, processes those concurrently across a bunch of nodes, and then aggregates the results.
The absolute easiest way to visualize this is like a highly efficient factory assembly line. The entire algorithm is chunked into 3 really distinct, easy-to-digest steps. Step 1, the map phase. Step 2, the shuffle and sort phase. And step 3, the reduce phase. Let's actually walk our data straight down this assembly line. Section 3, Phase 1, the map function, where we are splitting the data. Imagine a highly efficient manager delegating a massive workload. A primary master node takes an enormous raw input file and splits it into much smaller subdatasets, passing them out to individual worker nodes. And this is absolutely crucial. Instead of moving incredibly heavy data to a central processor, the processing moves to the data. Every single worker node processes its assigned chunk locally, and they all do it concurrently. Now, what's really fascinating about this output is how that raw, chaotic data is instantly filtered, sorted, and transformed into a highly structured collection of key value pairs. Literally, we've taken a mountain of unstructured data and mapped it into millions of uniform, neatly organized pairs that are now scattered across the entire cluster. Section 4, Phase 2, Shuffle and Sort. Handling the intermediate data. This intermediate phase happens entirely automatically under the hood, without any manual interference. Automated database-level routing intercepts all of that map output. The system sweeps through the worker nodes, collects every single intermediate record that shares the exact same key, and routes them together over the network to a designated reducer node. As a quick aside, in real-world clusters, this shuffle process is actually often the most resource-intensive part of the whole shebang. But check out the transformation here. We've gone from isolated, scattered key value pairs into a highly organized grouped array. All those separate values sharing a single key are now neatly bundled together. The format becomes one single key perfectly mapped to an array containing value 1, value 2, value 3, and so on. The data is now completely primed for the final step. Section 5, Phase 3, the reduce function, aggregating the results. Here is where we finally get the payoff. The reducer node accepts that massive grouped key value array and executes a mathematical aggregation operation across it. This could be computing a sum, finding an average, or running a count. With perfect rhythmic clarity, the reducer mathematically condenses that huge array into a single final value for that specific key, and then securely writes that final filtered output right back to the disk.
Section 6, the distributed power payoff.
Let's bring this all together. By dividing a large task into smaller subtasks, MapReduce elegantly condenses a massive, chaotic array of data into a single, useful metric. That perfectly summarizes the beautiful simplicity of this algorithm. We started with petabytes of chaotic data that would choke any traditional database. But by dividing that impossible task, mapping it into pairs, shuffling them, and reducing them, it literally turns chaos into logic. It's just a brilliant architecture.
So the next time you open a massive global app or run a complex search that somehow returns results instantly, take a second to appreciate the invisible architecture doing the heavy lifting. Ask yourself, how many worker nodes out there in a distributed cluster just mapped, shuffled, and reduced that data for you in the blink of an eye? It's pretty wild to think about. Thanks for joining me for today's explainer. Keep asking those questions, and I'll see you in the next one.